talking about moisture parameters and different types of temperatures, we got familiar, we learned a lot of new terms, and I think we stopped at pseudo-rheolytic gases. We discussed about what is rheolytic gases and what is pseudo-rheolytic gases. So this class, we will mostly talk about the cloud, how cloud formation, precipitation, and all those things. So to start with, just to so to start with, we will start with the term called environmental lapse rate. So lapse rate, I think we have discussed before. Lapse rate is basically the rate of change of temperature with respect to height. So it basically shows how, as we go up in the atmosphere, how the temperature is changing. So the first lapse rate that we are going to talk about is the environmental lapse rate. So generally the temperature in the troposphere decreases with respect to altitude. So we know, we learned about the vertical variation of temperature in the atmosphere in the first few classes. So basically in the troposphere, temperature decreases with respect to altitude, and this rate of decrease of temperature with respect to altitude is known as the environmental lapse rate, and this basically varies from place to place and time to time. Like morning, because the temperature will be high, the expansion troposphere will be expanded. The expansion of the troposphere, the height of the tropopause will be higher compared to the night. And basically tropics, because there is a higher temperature in the tropics, the extension of the troposphere will be high compared to the poles. So basically the lapse rate will vary from place to place and time to time. How the temperature is varying with respect to height is depends on the time at which we are considering and the place that we are considering. So generally the value for a given layer is basically determined from radius on the soundings. So I'll discuss what is radius on the soundings in the next slide. So generally the pattern is there will be a decrease in temperature with respect to height as we go up. So but in some part of the troposphere there may be a layer in which the temperature increases with altitude. So generally a decrease is seen with respect to altitude, but in some part of the troposphere there may be a layer in which temperature increases with altitude. So this is basically opposite to that what we generally expect. So this pattern is called as temperature inversion. So the layers at which we see an increase in temperature with respect to height are basically known as the inversion layers. So the environmental lapse rate is basically given by gamma, is represented by gamma, and is given by minus rho t by rho c. That is delta t by delta c, how the temperature is decreasing with respect to height. Negative sign shows that it is decreasing with respect to height. The value is actually negative. So that is environmental lapse rate. Now, so basically we measure the environmental lapse rate of the atmosphere using radius on the sounding scale. Let's see what basically is the radius on the sounding scale. So maybe you guys could have been familiar with this picture of a white big balloon, which we use to take atmospheric measurements. So radius only is basically a balloon-borne instrument for making measurements such as temperature, pressure, and humidity in the atmosphere. So generally this balloon will be filled with helium, which is basically having a density less than that of the atmosphere. So if we send this, if we leave the balloon in the atmosphere, because of its lower density, it rises in the atmosphere, and it can rise up to high altitudes of around 30,000 meters or 30 kilometers. That is above the troposphere, it can basically rise half of the stratosphere. So this radius on the flight generally lasts for around 2 hours, and during this time the radius on the can, as we are leaving it from we are launching the radius on from a particular place, but because of the wind speed and wind direction, it may get drifted. It can drift around 200 kilometers from the release point. From where we are releasing, it can go up to around 30 kilometers, and the entire flight will be taking time of around 2 hours. And also the radius only can drift more than 200 kilometers from the release. So what after a particular, so as the balloon is going up, because the atmospheric pressure is decreasing as it is going up, the balloon starts to get expanded. The balloon starts to expand, and when the balloon is expanding beyond its elastic limit, it basically bursts. So then it returns to the earth via a small parachute. So as we can see, the radio sonde has three most important parts. One is the hydrogen or helium balloon, and then it has a parachute, and then it carries the sensors that it needs to measure the parameters such as temperature, pressure, and humidity, like thermometer, barometer, and all those hygrometer, all those things. So it carries those instruments as well. So after bursting, after the balloon bursts after a particular height, what happens is that with the help of the parachute, it slowly descends in the atmosphere and returns to the earth. So that's how the radio sonde works. So with the help of radio sonde, we can get the vertical profile of temperature in the atmosphere at a particular place. So with the help of the vertical profile of temperature, we can actually calculate how it is decreasing with respect to height, basically the environmental latitude. So we find the environmental latitude of the atmosphere using instruments such as radio sonde. So this is basically in situ measurement. It is we are taking in situ measurements of temperature around the atmosphere. So that is about radio sonde. So I think environmental latitude is basically how the temperature is decreasing in the troposphere with respect to height, and the value is basically taken by radio sonde. Now, consider that a sample of dry air is rising vertically in the atmosphere, and because of the low pressure aloft, so the pressure will be decreasing with respect to height. We talked about it and we solved a lot of problems. Pressure is having an exponential decrease with respect to height. So as an air parcel is rising up in the atmosphere, because it enters regions of low pressure, what happens is that the parcel of air expands. Because of the parcel of air does work and expands and eventually cools down. Because during expansion, the parcel is doing work, so it basically cools down. According to the first law of thermodynamics, so it basically cools down. So the rate of decrease of temperature with respect to altitude of a dry air parcel. Dry air parcel in the sense the moisture content, there is moisture content in the parcel, but it is not saturated. It is still dry. So this rate of decrease of temperature with respect to altitude of a dry air parcel is dry adiabatic gas rate. This equation we had derived earlier. So the dry adiabatic gas rate of an air parcel in the atmosphere is basically G by Cp. G is the acceleration due to gravity and Cp is the specific heat at constant pressure. And we got the value of 9.8 degrees Celsius per kilogram. So this is how a sample of dry air vertically rising in the rising in the atmosphere cools down. So we have environmental latitude, which is the background latitude, or how in the atmosphere the temperature is decreasing. Now we are considering that suppose an air parcel in this atmosphere is rising up. So as an air parcel is rising up, this is how it goes. So that is dry adiabatic latitude. Now let's consider an air parcel which is moving up in the atmosphere. As we discussed, we now have two types of latitude. One is gamma, which is the environmental latitude, that's called AR, and then we have dry adiabatic latitude, This is the latitude of the parcel, and this is the background or environmental latitude. So let's consider the first condition, which is environmental latitude is less than gamma. Environmental latitude is a background. So basically, the rate of decrease of height with respect to height in the atmosphere is less than the rate of decrease of temperature with respect to height of parcel is moving in the atmosphere, it is undergoing a decrease of maybe 2 degrees Celsius for the same height. That's what it basically means. Gamma D is less, gamma is less than gamma D, or gamma D is greater than gamma. So basically, the dry air cooling at a faster rate than the atmosphere. So gamma is less than gamma D. So this is gamma. Suppose at this point O, there is an air particle. So at this point, both the particle and the environment are having the same temperature. Now consider we are rising an air particle from this point to a point A. So by doing some external work or by some method, some air particle which was initially at this point A has rise to this point, which was at the point O, was rise to this point A. So now the temperature of the particle is T, and at the same height, the temperature of the environment is T. So basically, at this point, when an air particle which was initially at the point O was raised to a height, was raised to another point A, in that case, the temperature of the particle is TA and the temperature of the environment is TB. So from the figure, we can see that TA is less than T. So now the particle is cooler than the environment. So generally, when a particle is displaced from its position, it adjusts at whatever height we have raised it or we have brought it down. It eventually matches with the surrounding pressure. The pressure will be same when we are considering an air particle surrounding. But in case of temperature, it generally changes. Hi, good evening. So I just started and I was talking about different lab rate and the stability in the atmosphere. So I started with environmental lab rate, which is basically how the temperature is decreasing in the troposphere. So we know, like, we have discussed the vertical profile of temperature before, and that decreases with respect to height. Then we know what is dry adiabatic lab rate. We have derived the equation for it. So basically, dry adiabatic lab rate is given by G by C2P. And yeah, so then we were discussing an atmosphere when the dry adiabatic lab rate is greater than the environmental lab rate. So in that case, suppose if we are rising an air particle which is initially at a point O to another point A. So at this point A, so this is basically gamma D, how the temperature of the particle is changing. And this is the profile for the environmental lab rate, how the temperature in the environment is changing. So when we raise the particle O from an air particle from O to A, at this point the temperature of the air particle is given by TA, whereas the temperature of the atmosphere is given by TB. So in this case, TA is less than TB. So the particle is having a lower temperature compared to the surroundings. So in this case, colder air is actually having more density than that of warmer air. Suppose if we consider the ideal gas equation, P is equal to rho RT. So P, as I told, like for the particle and the environment, the pressure will be the same. And R is also constant. So basically, rho and P, everything is constant. Rho and P are having an inverse relationship. So when the temperature is less, density will be high. So as I was telling, the parcel is now at the point at this height. The parcel is having a temperature TA, which is less than the temperature of the environment. So basically, since it is having a colder temperature, or since the parcel is cooler than the environment, it will have its density will be high. Density of the parcel will be high compared to that of the environment. So what will happen is that the parcel tends to return to its original level, since the parcel is having a higher density than that of the environment. So if we raise the parcel from O to A, the parcel after reaching this point, the parcel will have a tendency to come down to its original level. Now consider, suppose if this parcel is displaced downward. So if it is displaced downward, so let it, this be the point C. So now the parcel has been displaced downward. So this is the temperature of the parcel. Whereas at this point, the temperature of the parcel is T. Let it be. So initially we saw that when we raise the parcel from O to A, the temperature of the parcel was found to be less than that of the temperature of the environment, and the parcel had a sense, due to higher density, the parcel had a tendency to come down. Now consider that we are from its initial position O, we are displacing the parcel downward. So in that case, now the temperature of the parcel is Tc, whereas the temperature of the environment is Tb. And in this case, Tc is greater than Tb. So the parcel is warm. So if the temperature of the parcel is higher, it is supposed to have a lower density. So as I told before, the density and temperature are having an inverse relationship. So since the temperature is warmer, it will have a lower density than the surroundings. So in this case, the parcel will have a tendency to rise. So in this case, the parcel will have a tendency to rise and go back to its original level O. And in this case, the temperature will have a tendency to sink and go back to its original level O. So in both cases, the parcel of air encounters a restoring force after being displaced. So it doesn't matter in which direction we are displacing the parcel. In both cases, the parcel is basically having a tendency to come back to its original position, which is O. So it is encountering a restoring force, which inhibits the vertical mixing. So when this case, which is gamma less than gamma D, where is the environmental lapse rate is less than dry adiabatic lapse rate. So the restoring force that the parcel experiences when it is displaced from its original position is known as static stability. So in this case, the parcel is having a positive static stability, which means the parcel is having a tendency to come back to its original position. So in this case, an environmental lapse rate is less than the dry adiabatic lapse rate. The static stability is positive. Okay. Now consider this equation when the environmental lapse rate is greater than the dry adiabatic lapse rate. That is, the environment or the surroundings is cooling at a faster rate than the air passing. So in that case, let us see the dry adiabatic lapse rate, and this be the environmental lapse rate gamma. Dry adiabatic lapse rate is less than environmental lapse rate. So in this case, suppose this is the point O, and we are displacing the air parcel. Like earlier, we are displacing it from O to, in this case, parcel is of the parcel is T2, and temperature of the environment is temperature of the parcel PA and greater than PE, which means the parcel is still warmer than the surroundings and the density is less. So what will happen? The parcel will have a tendency to again rise in the atmosphere. Okay. So in the second case, when the environmental latch rate is greater than the air, which means the environment is cooling at a faster rate than the air parcel. So in that case, what happens is that when we displace the parcel from its initial position O to a particular height A, the temperature of the parcel is still down. So in that case, the parcel will have a lower density compared to the surroundings, and it will have a tendency to rise. So if displaced from its original position, it will have a tendency to again go up in that direction. So in this case, the restoring force is negative. There is no restoring force acting on the parcel. So in this case, the static stability is negative. Okay. So we talked about two conditions. The first one was then the environmental latch rate is less than the dry adiabatic latch rate. That is, the parcel is cooling at a faster rate than that of the environment. In that case, we saw that when the parcel is displaced from its original position, no matter when we are rising the parcel or we are trying to bring the parcel down, in both cases we saw that the parcel is having a tendency to go back to its original position, or it is having some restoring force is acting on the parcel. So in that case is basically known as positive static stability. So when there is a restoring force that is acting on the parcel, which tends to bring it back to its original position. In that case, the static stability is said to be positive, or there is positive static stability in the atmosphere. Now, in the second case, we consider the environmental latch rate is greater than dry adiabatic latch rate. So the environment is cooling at a rate faster than that of the parcel. So in that case, we saw that when the parcel is displaced from its original position, suppose if we are displacing the parcel, we are rising the parcel up in the atmosphere. So in that case, we found that even after reaching a particular height, the parcel is still warmer than the surroundings, which means the parcel is having a lesser density than the surroundings. So it will still have a tendency to rise up again in the atmosphere. So in that case, the restoring force is absent. So in that case, it is said to be negative static stability. So instead of returning to its original position, the parcel tends to rise further in the atmosphere. So that case is basically known as negative static stability. So these are the two cases. So in this case, we were considering a dry air, which means there may be water vapor in the parcel, but it is not saturated. Even though the presence of water vapor can be there or may not be there, the parcel is not saturated. Now let's consider what will happen if the parcel is saturated. So in case of an unsaturated air parcel, we saw that when the TLR was less than dry adiabatic latch rate, there was positive static stability, and the second case when ELR was greater than dry adiabatic latch rate, there was negative static stability. Now let's consider, suppose the parcel is saturated. Let's see what will happen if the parcel is saturated. So in case of saturated moisture, when we are trying to rise the parcel up in the atmosphere. So as we know, saturation means the parcel is holding the maximum amount of water vapor that it can hold. So when we rise a parcel in the atmosphere, it eventually cools down. So when a parcel cools down, its saturation vapor pressure decreases. So if we are rising an already saturated air parcel, what will happen is that the parcel will eventually cool down and it will exceed the amount of water vapor that it can hold. So eventually it will lead to condensation. The condensation of water vapor starts to happen within the parcel. There will be release of latent heat. During the condensation process, since the change of phase is from vapor to liquid, there will be release of latent heat. Latent heat of condensation will be released. So this heat will partly compensate for the decrease in temperature due to expansion during vertical motion. So we know when we are rising a parcel in the atmosphere, because of the expansion, the parcel eventually cools. In case of a saturated air parcel, even though when we are rising the parcel, there is supposed to be a cooling. Because of the release of latent heat of condensation, this decrease is partly compensated by this latent heat. So the saturated adiabatic lapse rate will be generally less than dry adiabatic lapse rate. SALR is less than V. So gamma is less than gamma because of the release of latent heat. So this is basically the equation for saturated adiabatic lapse rate. I think this has already been discussed in the NPTEL class, so I don't want to repeat the repetition. I hope the concepts are clear. So in the initial case, we saw when the environmental lapse rate is less than dry adiabatic lapse rate, the stability or the static stability was positive. The parcel had a tendency to come back to its original position. In the second case, when we saw the environmental lapse rate was greater than the dry adiabatic lapse rate, the static stability was negative. The parcel had a tendency to rise further up in the atmosphere instead of returning to its original position. So that was the second case. Now we are considering we are having a saturated air parcel. So saturated air parcel in the sense the parcel is already holding the maximum amount of water vapor that it can hold. So if we rise the parcel, again if we rise the parcel in the atmosphere, it will cool and the condensation will start to happen in the parcel. So even though as we go up in the atmosphere, the temperature is supposed to decrease for the parcel, because of the condensation that is happening in the saturated air parcel, the latent heat of condensation that is released during the process partly compensates this decrease in temperature. Okay, so basically the saturated adiabatic lapse rate. So how the temperature is decreasing in a saturated air parcel will be less compared to an air parcel which is dry. So that's the whole idea. Now let's consider the same thing, the stability of a saturated air parcel. As I said, if the air parcel is saturated, so if the air parcel is saturated, so we have an air parcel this is saturated, let it be at a height set in the atmosphere. So we are rising the parcel up at this time. So since it is already saturated, as we rise it again, the saturation vapor pressure decreases, condensation occurs, and there will be a release of the latent heat of condensation rate. L will be latent heat of condensation will be released during the process. So even though the temperature is decreasing as the parcel is going up, the temperature decrease is partly compensated by the release of latent heat or the release of heat. So basically, gamma S will be less than. And if the air parcels will be stable, neutral, or unstable, will depend on the environmental lapse rate that we are considering. What is the value of environmental lapse rate? So I think it is clear how the temperature is decreasing in case of a dry air parcel and in case of a saturated air parcel, and how the lapse rates are dependent on each other. Now consider this equation, then the saturated adiabatic lapse rate gamma is less than gamma. So the environmental lapse rate is having a value between dry adiabatic lapse rate and saturated adiabatic lapse rate. So consider this equation. So ELR is having a value gamma S less than gamma D. Then we are on the lab stage having a value between dry adiabatic lab stage and saturated adiabatic lab stage is known as conditional instability. See how the profiles will look. How the vertical profile of temperature will look in this case. So gamma S is having the lowest value, gamma S. Now gamma is having this in between. Now we have gamma D, which is higher than, which is having high speed. Let this be gamma D. It should not decrease. Gamma. So we have gamma, gamma S and gamma D. And the value of environmental lab state comes between ELF and so this one, this is close to the vertical, a saturated adiabatic lab state. This one in between the is the environmental lab state, and this is the dry adiabatic lab state. Let this be the starting point of our discussion, which is flow. This is temperature. So an air parcel at this point O, suppose it is raised to a temperature A. So initially when it is being raised, it is a dry air parcel. Let this be the temperature A. So its temperature is decreasing as it goes up in the atmosphere. So by some external force, we are rising the parcel, which was initially at the point O, to this point A. So now this is the temperature of the parcel, which is T. After reaching the point A, so as it is going up, it is eventually cooling. It is a moist air parcel, which means it is not saturated yet, but it has water vapor in that. It has water vapor inside the parcel. So as the air parcel is rising, its temperature is decreasing, right? As the parcel is rising, temperature is decreasing. And since it is a moist air parcel, at some point it will become saturated. As the temperature is decreasing, the saturation vapor pressure decreases. If you guys remember this, the saturation vapor pressure is directly proportional to temperature. Is inversely proportional. Is directly proportional to temperature. So as the temperature is decreasing, the saturation vapor pressure also decreases. So at this point A, let's just consider that the saturation it has reached the saturation at A. The parcel becomes saturated. So this point at the parcel where the parcel becomes saturated is known as the lifting condensation level. So this A is known as lifting condensation level. At L, the mixing ratio becomes saturation mixing ratio. The temperature is known as the dew point temperature, and the relative humidity is 100%. So by saturation, we mean the mixing ratio of the parcel is equal to the saturation mixing ratio, and the temperature at which saturation happens is known as the dew point temperature. As I have told earlier, when we decrease the temperature further below the dew point, then condensation starts to occur, and humidity will be 100%. So at this point, we know that the parcel is cooler than the ambient temperature. So if we consider the temperature of the environment, it is cooler than the environment. So suppose again rise the parcel to this point. So at A, the parcel is saturated. This level is known as the lifting condensation level, at which the saturation occurs when the temperature is equal to the dew point temperature. This point is known as the lifting condensation level. So suppose we rise the parcel again up from A to another point B. So if the parcel is again cooled from its saturation or from its dew point, what happens is that the parcel starts to condense. So when the parcel starts to condense, now the parcel, the rate of decrease of parcel with respect to height will be along this saturated adiabatic action. So once the parcel is saturated, it will follow the path of saturated adiabatic action. So if we rise the parcel further up from A, what happens is this condensation starts to occur. So at A, the parcel is saturated, that is the lifting condensation level. So it starts condensing and latent heat will be released. So what happens is that some amount of the latent heat released is used to warm the temperature. So the parcel will be, the rate of decrease of temperature with respect to parcel will be in the saturated adiabatic action. So when it reaches the point B, so this will be the temperature because it follows the saturated adiabatic, the profile for saturated adiabatic action. So at this point B, the parcel, the temperature of the parcel and the temperature of the environment are the same. So this means here. So this level is basically known as the lifting level of pre-convection. So suppose after crossing this point, the parcel will be following this profile. So after crossing this point, the temperature of the parcel is always greater than the temperature of the environment, which is this. This is gamma. So after crossing the point B, as it is going up, the temperature of the parcel will always remain greater than that of O. So after this level, after the point B, the parcel doesn't need an external force to rise up in the atmosphere because the parcel is warmer. The temperature of the parcel is warmer than the temperature of the environment. So after the point B, the parcel will rise on its own. Because of the release of latent heat of condensation, the temperature of the released heat is partly compensating for the decrease in temperature due to height. So after the point B, the parcel will rise by its own. It doesn't need an external force, or it doesn't need a lifting, which has to be given. So this level above which the parcel will rise by its own is known as the level of pre-convection. So at the point B, the temperature of the parcel and the temperature of the environment is the same. It coincides here. And after the point B, as we can see, that this is the profile for the environmental action, which is going like this. And this is the point for the saturated adiabatic action. It is always just like kind of divergence. So it is always greater than this temperature is always greater than the temperature of the environment. So it rises by its own. So that level is basically known as the level of pre-convection. Further, so up to the point B, the parcel was colder and denser than the ambient air, and then expenditure of energy was required to lift it. Once above the point B, the parcel develops a positive buoyancy that carries it upward even in the absence of further force lifting. We don't need to give a force lifting. And the level B is basically known as the level of pre-convection. And LFC depends on the moisture in the rising air parcel as well as the magnitude of the lateral current. So basically the height at which this level of pre-convection occurs depends on the moisture, how much moisture is available in the rising air parcel to condense, as well as the magnitude of the lateral. What is the environmental lateral? These two things are what the level of pre-convection depends on. So we learned two heights. One is the level of lifting condensation level. So this is the level at which saturation occurs. So if we rise the parcel further above lifting condensation level, we encounter the level known as the level of pre-convection. So after the level of pre-convection, the parcel doesn't need a lifting force, energy. We don't need to spend. There is no need of forced lifting because parcel will remain warmer than its surroundings, so it rises by itself. So this level is known as level of decomposition. So we learned two things, LCM and ES. And the conditional instability basically means the situation when the environmental lacerate is having a value in between the saturated adiabatic lacerate and the adiabatic lacerate. So gamma is less than gamma less than gamma. SAR less than environmental lacerate less than. This condition is known as conditional stability. I think we have cleared the terms. So we learned what is static stability and we learned what is conditional. Static stability, both profiles, like two conditions we learned, when ELR is less than DLR and when ELR is greater than DLR. What is happening with the disturbing force of static stability. And we come to saturated adiabatic lacerate, and we learned that the saturated adiabatic lacerate is always less than DLR because of the condensation and the release of latent condensation. Then we are considering the moist air parcel. This was not saturated initially, and we were lifting the parcel up in the atmosphere, and as it goes up, at some point it became saturated. That point was known as lifting condensation level, and further lifting led to the condensation in the air parcel. And after some particular point, which is basically known as the level of deconvection, the parcel remains warmer than its surroundings, and it kind of rise. It has a capability to rise on its own. There is no need of closed loop. That's all about instability, how it is in its profiles. So now let's move on to cloud formation, cloud droplets, and all those things. So we were discussing about air parcel, dry air parcel, condensation, all those things. So let's see how a cloud droplet is formed. So as we were talking about, once condensation starts, once an air parcel becomes saturated, it starts condensing. And how the condensation is occurring, how cloud droplets are forming. Let's have a look into that. So generally an ordinary cloud droplet is extremely small. When we talk about cloud droplets, it is basically having an average diameter of 20 micrometers. So the cloud droplets generally formed by the condensation is having a diameter of 20 micrometer or 0.02 centimeter. And generally a rain droplet that we are talking about will have a diameter of around 5 millimeters, which is basically 5,000 micrometers. So it is very much smaller than a typical rain drop. The cloud droplets that are forming due to condensation is very much smaller than a typical rain droplet. So let's see how this droplet is growing in size and how it is reaching the size of the rain droplet. So if a cloud droplet is in equilibrium with its surroundings, the size of the droplet does not change because the water molecules. So as I told, there is an air parcel, it became saturated, and now the condensation will start over. So once the condensation starts to occur, so we learned like when an air parcel is saturated, the rate of evaporation and the rate of condensation will be equal. So when we are saying that an air parcel is saturated, it means like the amount of water vapor molecules that is evaporating is equal to the water vapor molecules that is condensing. There is an equilibrium that is existing between the rate of evaporation and the rate of condensation. So at this point, when the droplet is in equilibrium, these two rate of evaporation and rate of condensation are equal. So the droplet size kind of remains same. Suppose if the droplet is not in some rate, like either the rate of evaporation or the rate of condensation is greater than the other, then the droplet size, I rate of condensation, rate of evaporation are equal. So the droplet size remains constant. So once if the droplet is not in equilibrium, either condensation or evaporation dominates, and depending on which is dominating, if condensation is dominating, the droplet will eventually flow, and if evaporation is dominating, the cloud droplet will eventually the size of the cloud droplet will eventually decrease. So consider a cloud droplet which is in equilibrium with its surroundings. Total number of water molecules around the droplet remain fairly constant and defines the droplet saturation rate. So as I told, if a cloud droplet is in equilibrium, the amount of water vapor molecules or the saturation vapor pressure of the droplet will be a constant. So the amount of vapor molecules surrounding the cloud droplet will remain fairly constant if the cloud droplet is in equilibrium. And this defines the droplet saturation. And we know that the droplets or cloud droplets are generally having a curved structure. It is not a flat surface, it is having a curved surface. Whereas when we are considering a flat surface, the saturation vapor pressure with respect to a flat water surface is generally less than the saturation vapor pressure with respect to a curved surface. So for a cloud droplet to form, or for a cloud droplet to be in equilibrium, the number of water vapor molecules required to maintain for the survival of the cloud droplet is generally higher, greater compared to that of a flat water surface. Because water molecules are less strongly attached to a curved water surface, hence they evaporate more readily or more rapidly. Since the droplet size is very small and it is weakly held to the droplet, it has a higher tendency to escape from the droplet. So to keep the droplet in equilibrium, more water molecules are needed around it to replace those molecules that are constantly evaporating from the surface. So if we want the cloud droplet to survive, more vapor molecules is required. As the vapor molecules above the cloud droplets are condensing and forming cloud droplets, more water vapor molecules are required to compensate for this condensation. So generally, smaller cloud droplets require even greater vapor pressure to keep them from evaporating air. If the number of water molecules surrounding the cloud droplet decreases, water vapor molecule decreases, saturation vapor pressure decreases, and the cloud droplet will eventually evaporate. So only when both rates are equal, like rate of evaporation and rate of condensation are equal, then only the cloud droplet survives. So the smaller the droplet, more the saturation vapor pressure required for the cloud droplet. So if the cloud droplet that is formed is very small, the number of water vapor molecule that is required for the survival of the cloud droplet is very high. So the relative humidity must be several hundreds, or the droplets should have a greater supersaturation for smaller droplets to survive. In case of smaller droplets, curvature is high, saturation vapor pressure is high, which means the number of water molecules that is required around the cloud droplet is higher for the cloud droplet to survive. So we consider, depending upon the droplet diameter, how much relative humidity is required for a droplet to survive. We can see that as the droplet diameter is increasing. So as the droplet diameter is increasing, the curvature of the cloud droplet or the curvature of the droplet is decreasing. So a smaller droplet is having a greater curvature compared to that of a smaller droplet is having a greater curvature compared to that of a bigger droplet. In case of a bigger droplet, the curvature is less. So in this case, the ES will be less. In this case, the saturation vapor pressure will be higher. So the survival of this droplet, the number of water vapor molecules that is required, or the number of, or the supersaturation level that is required, is several hundreds. But in this case, when the droplet is larger, this is less. The relative humidity is comparative. Relative humidity that is required for the survival of this droplet is comparatively less. So as the droplet size decreases, or as the curvature decreases, as the curvature is decreasing, which means the droplet size is increasing, the relative humidity that is required for the survival of the cloud droplets is less. So for droplets which is having a droplet diameter of around 1 micrometer and 1 micrometer or something, the relative humidity that is required is around 100, more than 100, like 100.4%. So in normal atmosphere or in general natural conditions, it is very much unlikely to reach this high levels of supersaturation. So when the droplet size is less than 2 micrometers, the relative humidity must be above 100% for the droplet to survive. As droplet becomes larger, the effect of curvature is also decreasing. And for a droplet whose diameter is greater than 20 micrometers, the curvature effect is so small that the droplet behaves as if its surface was flat. So as the curvature is decreasing, the saturation vapor pressure is also decreasing. So just as relative humidity is less than that required for equilibrium, permit a water droplet to evaporate and shrink. Those greater than the equilibrium value allow the droplet to grow by condensation. So as the droplet is growing, the chances of survival is very high. But when the droplet is very small, the chances of survival is very less. It needs very high level of supersaturation for it to survive. So naturally, a droplet which is formed without the help of any other particle, or which has formed due to homogeneous nucleation, are having a diameter which is very small, so it is difficult to survive. So homogeneous nucleation is basically due to just collisions between the water vapor molecules in the vapor phase. Small embryonic water droplets are formed, but because of the smaller size of these droplets, it is very difficult for them to survive. As I said, smaller the droplet, higher the supersaturation that is required for the water droplet to survive. So, generally in that, so this process in which the droplets form by the chance collisions between the number of molecules or without the help of an external body is known as homogeneous nucleation. So, homogeneous nucleation requires very high level of supersaturation to form a cloud droplet or water droplet. So, generally in the atmosphere, how droplets form is through the process known as heterogeneous nucleation. So in case of heterogeneous nucleation, the water vapor molecules condense on top of particles known as cloud condensation nuclei. So if you guys will be remembering, we talked about aerosols in the first or second class. So basically, aerosols are tiny solid or liquid particles that are suspended in the atmosphere. So there are different types of aerosols like dust particles, sea salt, black carbon. So some of these particles are hygroscopic in nature. Hygroscopic in the sense they have a affinity towards water. So those some of the aerosols which are having an affinity towards water, it behaves as a platform for the water droplets, water vapor molecules to come and condense on top of it. So those those cloud droplets which are formed due to heterogeneous nucleation will be a larger size compared to that of the droplets that have been formed due to homogeneous nucleation. So generally in the atmosphere, the water droplets are formed due to the process known as heterogeneous nucleation, where the water vapor molecules condense on top of aerosols, which activated aerosols, which are basically known as cloud and condensation nuclei. So on top of cloud condensation nuclei, water vapor molecules come and then condense. So the cloud droplets that are formed due to heterogeneous nucleation will be having a larger radius. So the chance of survival for these particles are comparatively higher. Whereas in case of homogeneous nucleation, where the water droplets are formed by the chance collision of number of water molecules in the vapor phase, so they form very small water droplets. So the supersaturation that is required for those small droplets to survive are very much high, which actually doesn't occur in the atmosphere. So generally, cloud droplets are formed in the atmosphere through the process known as heterogeneous nucleation. And what it is clear, there are two types of nucleation: homogeneous nucleation, in which the cloud droplet molecules are formed without the help of an external agent. They just by colliding, the vapor molecules collide with each other and then form small droplets. So as we just saw, the amount of supersaturation required for a smaller droplet to survive because of its higher curvature is very much high. So that much high supersaturation doesn't exist naturally in the atmosphere. So the chances of formation of cloud droplets through homogeneous nucleation is very less. Whereas there is another type of nucleation which is known as heterogeneous nucleation, in which the aerosol particles, a subset of not all aerosol particles can act as cloud condensation nuclei. So those aerosol particles which can perform or which can act as a platform for the water vapor molecules to condense upon it are known as cloud condensation nuclei. So those aerosols which is having an affinity towards water generally act as cloud condensation nuclei. So the process by which the water cloud droplets are formed on top of the CCN or cloud condensation nuclei is known as heterogeneous nucleation. So generally in the atmosphere, the cloud droplets are formed through the process known as heterogeneous nucleation. So I just wanted to stress upon three terms. One is homogeneous nucleation, the other one is heterogeneous nucleation, and the third one is the curvature effect. The fact that higher the curvature of the droplet, that is, smaller the droplet size, higher the curvature, higher the saturation vapor pressure required for the droplet to survive in the atmosphere. So as the droplet grows in size, the relative humidity required for the survival of the cloud droplet reduces. So this phenomenon is basically known as the curvature effect. Smaller droplets, higher the curvature, higher the saturation vapor pressure required for survival, higher the supersaturation. I think it is here. Homogeneous nucleation, heterogeneous nucleation. What is cloud condensation nuclei? The subset of aerosols that can act as a platform upon which the water vapor molecules can condense is known as cloud condensation nuclei. Generally, the aerosols which are having an affinity towards water acts as cloud condensation nuclei. And then what is curvature effect? Curvature effect is basically smaller the droplet, higher will be the curvature. So the amount of supersaturation required for the droplets to survive is very low. And generally through homogeneous nucleation, the droplets formed are having a very smaller size. So the equation, the mathematical representation of curvature effect is basically given as log E by ES. So that E is the saturation vapor pressure of the parcel at a radius r, not saturation vapor pressure, r, the vapor pressure of the parcel at having a radius r, and ES is the saturation vapor pressure that it requires. Log E by ES is given by 2 sigma RNKT or if we are considering number of molecules. If we are considering number of moles, then it can be R. Instead of Boltzmann constant, it will be the specific of gas constant. So K is if we are considering number of molecules, and when we are considering number of moles, the endless number of moles, it becomes R. Instead of K, it will become R. So 2 log E by S is given by 2 sigma R NKT, where R is the radius of the droplet, N is the number of molecules in this case, K is the Boltzmann constant, and E is the temperature. Or 2 sigma R N R into T. In this case, N will be the number of moles and R will be the specific gas constant. So this is known as Kelvin's equation or the mathematical representation of curvature. Again, the derivation have been taught in the class. I just wanted to stress upon these new terms. These concepts of homogeneous nucleation, heterogeneous nucleation. What is curvature effect and what is condensation effect? So this is the equation for the mathematical representation of curvature effect. This equation is basically known as the Kelvin's equation. Yeah. So now, as I told, in the atmosphere generally clouds form by the process known as heterogeneous nucleation, not homogeneous nucleation. So suppose there is a cloud condensation in here, and so because of supersaturation that develop in natural clouds due to the adiabatic agent of air rarely exceeds a few percentage, it follows from the so if droplets of pure water as large as 0.01 micrometer in radius are found, like it requires very much high supersaturation levels to survive. So generally, the cloud droplets in the atmosphere forms through the process known as heterogeneous nucleation. So those aerosols that are vegetable or which is having an affinity towards water can act as senders upon which water vapor can condense. So droplets can form on these particles at much lower supersaturation than those required for homogeneous nucleation. So in case of heterogeneous nucleation, the level of supersaturation that is required for the formation and growth of cloud particles is very much less compared to that in case of homogeneous nucleation. So some of these particles can act as CCN are soluble in water. Some of these CCN are soluble in water. So as the water vapor molecules are condensing on top of it, the material or the cloud condensation material dissolves in the water, dissociates and dissolves. So consequently, they dissolve wholly or in part when water condenses onto them. So that is solution droplet is formed. Instead of a pure water droplet, a solution droplet which will have the CCN dissolved on it will be formed. So the saturation vapor pressure of water adjacent to a solution droplet, that is a water droplet containing the dissolved material, is less than that of a pure water droplet on the same. Suppose there is a solution water droplet, which means it is having the dissolved CCN, and there is a pure water droplet. So the saturation vapor pressure in this case, let it be E, and E dash, and the saturation vapor pressure of a pure droplet. So this will be less than the saturation vapor pressure of a pure droplet. So in case of solution droplet, or when the CCN is dissolving in the water droplet, the saturation vapor pressure of the droplet will be less than the saturation vapor pressure of a pure droplet at the same size. So dash will be less than. Generally, the aerosols or CCN that has this property as NaC, like NaCl, ammonium sulfide, and all those. Ammonium sulfide and all those chemicals or components. So this reduction or the fractional reduction in the water vapor pressure is given by E dash by E is equal to I. That this is the mole fraction. The E dash is the saturation vapor pressure adjacent to a solution droplet containing a mole fraction chi W of pure water. So this is the mole fraction of pure water. How much water is present in that solution? Mole fraction of pure water. And E is the saturation vapor pressure. E dash saturation vapor pressure of solution droplet. And E is the saturation vapor pressure of pure droplet, pure water droplet. So mole and chi W is the mole fraction of pure water. The mole fraction chi W is represented as, this is the mole fraction of water droplet. It will be the number of moles of water present divided by the number of moles of solute plus total number of moles which water is there in the solution. So the solute plus NW. So this will be the mole fraction. So consider a solution droplet of radius r. Let the radius be r, and contains a mass m of dissolved solute. So m is the mass of the dissolved solute in kilogram. Okay, so we have both solution droplet and pure water droplet will be having the same radius, which is given by r, and let m be the mass of the dissolved solute, which is represented in kilogram, and NW is the molecular weight of water, and MS is the molecular weight of solute. Okay. So the mole fraction of water, IW, is given by NW by NS plus NW. So N is the mass of the solute present. So the number of moles, we want to find the number of moles of solute, right? Number of moles is given by I into 1000 M by M. I is the ions, that is number of ions that has found. So basically it dissociates. If it is NaCl, it dissociates into Na plus and Cl minus ions. So how many ions has found? That determines the number of moles of the solute. So I into, mass, so if we want to find the number of moles, if M is the given mass of the solute, so M by molecular weight will give the number of moles into 1000 because M was given in kilograms. So number of moles of the solute is given by I into 1000 M by MS. Now we want to find the number of moles of water. Number of moles of water. So in case of water, this M, or how many moles of water is available, is not given. So let's consider the density of the water is rho dash. So if density is given, mass can be written as 4 by 3 pi r cube into rho dash, volume into density. So this is the mass of the water minus n. In the solution, how much number of moles of water is available will be given by the mass of water vapor minus the mass of solute that is present. So 4 by 3 pi r cube minus n divided by the molecular weight of so number of moles of solute is given by I into 1000 m by ms, where m is the mass of the solute and ms is its molecular weight. And in order to find the number of moles of water, what we did was we don't know how much what is the mass of the water that is in the solution, but let's consider the density of the water to be rho dash. So the mass is given by density into volume. So 4 by 3 pi r cube into rho dash is the mass of the water. And within the solution, how much is available? We have to subtract it with the mass of solute. So 4 by 3 pi r cube rho dash minus n divided by the molecular weight of water will give the number of moles of water. So now if we substitute for chi w, so this is basically ns and this is nw. So if we substitute here, chi w is given as nw, we can write it as 4 by 3 pi r cube rho dash minus n divided by mw by I. Here also that 1000 will come because again this m is given 1000. So that 1000 and 1000 will be so I n by ms plus 4 by 3 pi r cube rho dash minus n. So this is the mole fraction of water in the solution. So if we make the denominator common, like I n and w plus 4 by 3 pi r cube rho dash minus n into ms divided by ms m. So the nw and nw will become 4 by 3 pi r cube rho dash minus n into divided by I n nw plus 4 by 3 pi r cube rho dash minus n. So we'll write it in the inverse form. So we take it down. Write it as I n nw plus 4 by 3 pi r cube rho dash minus n divided by 4 by 3 rho dash minus n the whole so this will eventually 1 plus I n nw by 4 by 3 pi r cube rho dash minus n into n. The whole inverse. So this is basically so E dash by 1 by 1 plus x. So this is basically x. This is inverse. So it is basically in the form of 1 by 1 plus x. So 1 by 1 plus x can be written as 1 minus x. So it can be written as 1 minus I n n w by ms into 4 by 3 pi r dot dash. It can be written as d dash by ds. Saturation vapor pressure of the solution droplet. Saturation vapor pressure of the solution droplet divided by the saturation vapor pressure with respect to pure water droplet is given by 1 minus I n nw by ms into 4 by 3 pi r. So this is basically known as a Raoult's law. Raoult's law basically gives the fractional reduction in the water vapor pressure of the solution droplet compared to that of the pure droplet. So this equation is basically known as the Raoult's. So it basically says that the saturation vapor pressure of water adjacent to the solution droplet is less than the saturation vapor pressure of a pure same size, and the ratio of them is basically given by the mole fraction of water in the solution. So this is Raoult's law. So actually we can combine the Raoult's law and Kelvin's law. Kelvin's law was given as E by Es is equal to sigma by log E by Es is equal to log E by Es is equal to 2 sigma by R n. So E was the radius of the droplet that has formed, and Es is the saturation vapor pressure. So if we combine both these equation, E by Es will become E by Es can be written as. So this shows how the saturation vapor pressure required for a droplet of radius r, considering the curvature, and this shows the reduction in saturation vapor pressure of a droplet which is formed through solute effect, or which is formed through heterogeneous nucleation, and it's formed through a solution. So E by Es is given by exponential of 2 sigma by NKTI into 1 minus INNW by 4 by 3 by ms into 4 by 3 pi r to the rho dash so the total equation so suppose if we plot the variation of relative humidity adjacent to a solution droplet as a function of its radius, we obtain the Fowler's curve. So this is basically known as the Fowler's scale. It combines the effect of both Raoult's effect and the Kelvin effect or the curvature effect. The green line, this green line basically shows the this green line basically shows the curvature effect, and this red line shows the Raoult's effect. So in case of the green line, as we told, cloud droplets are for small droplets having very small size. The saturation ratio that is required for the droplet to survive is very high. So this curve represents that curvature effect. So as the diameter of the droplet is reducing, the saturation ratio, basically E by ES, is also getting higher. So saturation required is becoming very high. Whereas in case of the Raoult's effect, for smaller droplets, even though the saturation level is less, the droplet can still be formed. And similarly, as the size of the droplet is increasing, the rate of supersaturation required is also increasing. So this is basically having a opposite kind of effect. So the combination of both Raoult effect and Kelvin effect is giving the curve which is known as the polar curve. As the size of the droplet is increasing, after some particular point, both of the lines are coinciding. So once the droplet has attained the size which is larger enough, then even if the saturation ratio is kept as a constant, the droplet still grows. So that radius is basically not the typical radius of the. The combination of both curvature effect and solution, both sometimes known as a polar. The next one that I wanted to talk about was the formation of precipitation, like the two processes, collision coalescence and the Bourgeois emission process. I think it has already been discussed in the class, so I just wanted to kind of revise. So basically, in the atmosphere, the typical size of the cloud condensation nuclei is 0.02 micrometer, and the size varies depending. So different type of nuclei are present in the atmosphere. There are 8 nuclei, there is intermediate large nuclei, there is giant nuclei, depending on the size of the aerosols that is available. So in case of 8K nuclei, the radius of the particle is less than 0.2 micrometer, and in case of large nuclei, the radius is coming between 0.2 and 10 micrometer, and in case of giant nuclei, the radius is greater than 1 micrometer. So generally, the process how we have reached it here. So the condensation nuclei is having a size of 0.2 micrometer, and then once the droplet is formed, so for the droplet to form or the droplet to survive, it needs a radius of minimum 20 micrometers. So that is the typical size of a cloud droplet. And again, if it has to fall down as precipitation, the radius that is required or the size that is required for typical raindrop is around 2000 micrometers. So from 0.02 micrometer, by the condensation and with the help of heterogeneous nucleation, solution effect and all those things, the droplet eventually formed and grew to a size of 20 micrometer. Now again the droplet has to increase its size to around 2000 micrometer for this droplet to fall from the atmosphere as precipitation. So let's see how this increase in size of the droplet is increasing, how the cloud droplet is becoming rain droplet, and how it is finally falling on the atmosphere. So in case of warm clouds in the sense, in case of, I hope you have learned about the different types of clouds, how the properties are varying with respect to height. There are low clouds, there are middle clouds, there are high clouds. We have already learned that. There has been already talked in the class what are the different types of clouds, which represent rain clouds and all those things. So generally, for clouds which are having the cloud tops which are warmer than minus 15 degrees Celsius are known as warm clouds, and the process in which the precipitation is formed in these clouds is through the collision coalescence process. So warm clouds basically have cloud tops which is warmer than minus 15 degrees Celsius. So in order to produce a rain droplet, many collisions are necessary between droplets of non-uniform size. So suppose we have a cloud which consists of only small cloud droplets. So as in this case, we have a cloud with small cloud droplets which are having uniform size. The droplets are less likely to collide as they fall slowly at about same speed. So within the cloud, after the formation, the cloud droplets are falling down. So as the cloud droplets are falling down, depending on the size of the droplet, the speed of the cloud droplets change. So the droplets having a higher size will have a higher speed while forming. So in case of smaller droplets of uniform size, the speed at which the droplets are falling within the cloud will be the same. So if all the droplets are having the same size, the chances of collision between the droplets is very less because they are falling at the same speed. So even though these droplets, some of the droplets do collide frequently, but they don't stick together because of the strong surface tension that holds together each tiny droplet. Because in the case of small droplets, the surface tension that it has is very high. So in that case, even if these small cloud droplets happen to collide with each other, the chances that they will stick together is very less. So now consider another cloud which is having different size of cloud droplets. So they have both small cloud droplets and they have large cloud droplets as well. So consider a cloud which is composed of different size of cloud droplets. Larger droplets will be falling at a rate faster than the smaller droplets. So these larger droplets will be having a greater speed compared to that of the smaller droplets. So in this case, the number of collisions and after collision, the number of the probability of the small droplets to stick together to that of the large droplets is also high. So the chances of more cloud growth or more collision and coalescence is in case of a cloud which is having droplets of different size. So as the cloud droplets or these droplets falls, the speed of the falling drop increases. As it is falling down, its speed kind of increases until the air resistance equal to the pull of gravity. So basically, in a falling droplet, the forces that is acting is there is the gravitational force which is acting downward, and there is also this air resistance that is acting on the cloud. So then these two forces become equal. So generally, when the droplet is falling, speed increases as it is falling down, and at one particular point, the air resistance that is acting on the droplet, and the gravitational force which is pulling it down becomes equal, and at that point, it starts to fall at a constant velocity, which is basically known as the terminal velocity. So some of the factors for this collision. So even if the drops collide with each other, the chances of coalescence is less. So what all factors can actually increase the coalescence? Let's look into that. So generally coalescence is enhanced when the droplets are having opposite charges. So if the falling droplets are having opposite charges, the chances of coalescence is high. And also it also depends on the time that is spent by the cloud droplet within the cloud. How much time the cloud droplet is actually spending within the cloud also determines the size of the cloud droplet. So suppose there is a cloud droplet which is having a diameter of 100 micrometers. So generally within the cloud there will be strong updraft that is happening because of the latent heat release and convection that is happening within the cloud. So there will be strong updraft. Updraft is basically that positive vertical velocity within the cloud. So as a cloud droplet which is having a size of 100 micrometers is caught in this updraft, it goes up, and by going up it is undergoing this collision and coalescence, and after undergoing this much process, it will increase in its size around 1000 micrometers. So as the droplet rises, it collides with and captures smaller droplets in its path and grows until it reaches a size of about 1000 micrometers. So at this point, the updraft of the cloud is just able to balance the pull of the drop. At this point, both the updraft acting and the gravitational pull is kind of same. And after this, so at this point the droplet is remaining suspended until it grows just a little bigger. So now with this mass, the forces that is acting on the droplet, that is the updraft and the gravity, is actually in balance. And so the droplet remains suspended in the atmosphere. Once the fall velocity of the drop is greater than the updraft velocity, once the mass increases and the fall velocity also increases. So once it becomes greater than the updraft, what happens is that the drop slowly descends. So it was suspended and then it starts slowly, it will start coming down. So again, as the drop is falling, larger droplets are captured by the falling drop, which then grows bigger. So by the time the drop reaches the bottom of the cloud, it will be a large raindrop with a diameter of size 5,000 meters. By coming out it would have reached that stage when it could be called a raindrop. So from 100 micrometers, how much time it is actually spending in the cloud. If it is spending more time, the chances of collision and coalescence is very high. So the larger will be the size of the droplet, and it also depends upon what is the updraft velocity within the cloud. If it is higher, more time the more time this droplet can spend within the cloud, or it will remain suspended for a longer time compared to a cloud which is having a lower updraft velocity. So more the time that is the that is more time the droplet is spending within the cloud, higher will be the droplet size. Chances it can grow that much. So that also depends on if it will turn into a raindrop. So generally thick clouds, thick things which is having a higher vertical extension. With strong updraft maximizes the time cloud droplet. So if it is basically a thick cloud with very strong updraft, it maximizes the time the droplet spends in the cloud and hence the size to which they can grow. So the most important factors in the generally the most important factor is basically the cloud's liquid water content. How much liquid is actually available within the cloud for condensation to occur. So within a cloud with sufficient water, other significant factors include the range of the droplet size. What, like as I told, it is important for the droplets to be of different size for effective collisions and collision coefficients to occur. So there should be larger droplets, there should be smaller droplets, and only more efficient collisions will happen. So one is the range of droplet sizes. The second is the cloud thickness. The most important thing is the liquid water content, how much water is available within the cloud for condensation and all those things. And then other than that, range of droplet size. What are the different size ranges that is available within the cloud. Second one is the cloud thickness. As I said, if the thickness is high, the time that the droplet spends within the cloud will also be high. The updraft, stronger the updraft velocity, then also it can the cloud droplet stays within the cloud for a long time. And fourth one, the electric charge of the droplet. As I said, if the during collision, the chances of coalescence is more if the droplets are having different charges. Electric charges. So these are the four things other than liquid water content that is important for cloud droplets to collide and form rainwater droplets. So next is the ground process, which is basically the process by which warm cloud process or collision coalescence process is mostly prominent in tropics where there is warm clouds. Whereas the Berggrund emission process or the ice crystal process is important in middle and high latitudes. So in middle and high latitudes, the chance of forming, because those places the clouds extend to that to above the 0 degrees Celsius isotherm. So the chances of and their precipitation is also, they have snow, hail, and all those things. So these clouds and this process is mostly important in middle and high latitude regions. So the clouds that extend upward into regions where the air temperature is well below freezing Celsius. This well below 0 degrees Celsius is known as cold clouds. So which has so as I so warm clouds we told earlier, the clouds that are having a cloud top temperature of minus 50 degrees Celsius is known as warm cloud. And in this case, the clouds that extend upward into the atmosphere where the air temperature above 0 degrees Celsius isotherm is known as cold clouds. So the precipitation process in cold clouds is known as the Berggrund process or ice crystal process. So consider a cumulonimbus cloud. If you have, if you remember, cumulonimbus cloud is a vertically developing cloud, which is the vertical extent will be very high. So suppose there is a cumulonimbus cloud and the base of the cloud. So this is where the cloud starts to form. So this, let this be the freezing level, or this is the 0 degrees Celsius isotherm. Above this, the temperature is falling below 0 degrees Celsius. Chances of formation of cloud ice is more above this 0 degrees Celsius. So at this level, till the 0 degrees, this is the base of the cloud. Till the 0 degrees Celsius level, there is only liquid water present in the cloud. So as we go up in the atmosphere, the temperature is decreasing. Above the 0 degrees Celsius isotherm, just above the 0 degrees Celsius isotherm, only water droplets will be existing. And water droplets existing below freezing are referred to as supercooled droplets. So if the water, generally the water is supposed to cool below 0 degrees Celsius, but if you take the cloud just above the 0 degrees Celsius isotherm, still the vapor will be existing in form of water droplets only. So those water droplets are basically known as supercooled water droplets. So as we go up, in between the middle layer, we will be able to see some supercooled water droplets and some ice particles. But still the amount of ice particle will be very less even in this layer. And again, as we go up at the topmost layer, there will be only ice. So that happens above when the temperature is dropping below minus 40 degrees Celsius. So at that height, we will only find ice crystals. So the region of cloud where only ice crystals are found is called glaciated. So this region of the cloud is basically said to be glaciated. So this region only contains ice particles. So this is found above the minus 40 degrees Celsius isotherms. So how these ice particles are formed? So generally, when we talked about water droplets, liquid water droplets, we told that they're generally formed by heterogeneous nucleation. So some of the aerosol particles act as a platform on which these water vapor molecules can condense and form water droplets. So in case of ice formation, just as liquid droplets form on condensation nuclei, ice crystals may form on particles called ice nuclei. So those particles upon which the vapor can condense and form ice particles are known as ice nuclei. But different from CCN or cloud condensation nuclei, the ice forming nuclei available in the atmosphere is very less. So one of the example of ice nuclei is clay minerals such as kaolinite. Clay minerals such as kaolinite can act as ice nuclei, but the amount of ice nuclei that is available in the atmosphere is very much less compared to the condensation nuclei. So that's why the formation of ice is comparatively difficult If water vapor gets deposited directly and directly it becomes instead of that water phase. So these are called deposition nuclei. In this situation, water vapor directly changes into ice without going through the liquid phase. So there will be some ice nuclei upon which the water vapor condenses and directly form ice without having the intermediate liquid phase. Vapor directly to ice. So those type of nuclei or those type of particles which are capable of doing that is known as deposition nuclei. And in some other particles, the ice nuclei that promote freezing of supercooled droplets are called freezing nuclei. So one is from vapor to ice, and another one is there will be some nuclei upon which these water droplets will come and condense. So as I said, as we go in this cloud, we have both supercooled water droplets and ice at in this height. So these supercooled water droplets, which is basically the water droplets below the freezing level, will collide, will condense on the ice nuclei and form ice particles. The droplets will condense and then form ice. So those nuclei are basically known as freezing nuclei. And among the freezing nuclei, in some cases, what happens is that these particles, when collide with supercooled droplets, will form the ice particles. So those nuclei are basically known as contact nuclei. So there is deposition nuclei, there is contact nuclei. So in case of deposition nuclei, the water vapor molecules condense on the ice nuclei and directly form ice particles. And in case of contact nuclei, the supercooled water droplets present in the atmosphere, present inside the cloud, collide with the ice particles and then form ice crystals. So that is contact nuclei and deposition nuclei. So now let's look at how the ice particles grow. So now the ice particle has formed. Now let's look at how these ice particles are growing within the cloud. So suppose there is a cold supercooled saturated cloud. Since the air is saturated, both the liquid droplet and the ice crystal are in equilibrium. So as we were discussing, as we already know, if we are telling that a droplet or an ice crystal is saturated, it is basically the rate of that saturation, the rate of evaporation, rate of condensation should be equal. So that is the basic condition for equilibrium or saturation. So both in case of liquid water droplet and in case of ice crystal, this condition should be maintained. So the number of molecules leaving the surface of both the droplet and the ice crystal must be equal to the number of molecules that is returned. So the water droplet is there is evaporation as well as condensation is happening. This is equal. And as well as on top of ice crystals also the same thing is happening, evaporation and condensation. So this has ESW, which is the saturation vapor pressure of water vapor, and this has ESI, which is the saturation vapor pressure of ice. So the molecules that escape for the molecules to escape from the water droplet is comparatively easier compared to that of ice. So in this case, this evaporation is easier compared to that in case of ice crystals. So what happens is that the saturation vapor pressure required for the water droplets to survive is greater than the saturation vapor pressure that is required for the ice crystals, because the rate of evaporation from the ice crystals will be less compared to that of the rate of evaporation from water droplets. So what happens is that consequently more molecules escape from the water surface at a given temperature, requiring more in the vapor phase to maintain saturation. So more water vapor molecules will evaporate from the water droplet. Whereas at the same temperature, the saturation vapor pressure over the ice will be less. So from the ice particle, the rate of evaporation will be less. So at the same temperature, both of these things are happening. So, more water droplets are evaporating from the are evaporating from the water droplet, whereas the rate of evaporation is comparatively less in case of the ice crystals. So what happens is that difference in vapor pressure. So basically ESW is greater than ESI. Saturation vapor pressure of water is greater than the saturation of vapor pressure of ice. So the number of vapor molecules that is required for the water droplet to survive is greater than the number of water vapor molecules required for the ice crystal to survive. So this difference in vapor pressure causes the water vapor molecules to move from the water droplet towards the ice crystal. So what happens is that the water vapor molecules move from the water droplet towards the ice crystal. So the removal of water molecules reduces the rate of water flow above the water droplet. So the thing is like the water droplet needs more water vapor molecules for it to survive, but because of the lower saturation vapor pressure, water vapor molecules starts to move from the water droplet towards the ice crystal. So now it is now out of equilibrium. So it won't be able to reach the saturation vapor pressure that it requires. So eventually the water droplet starts to evaporate. So whatever is getting evaporated from the droplet is actually replenishing the supply of water vapor over the ice crystal. So this evaporation of formed water droplets will provide a continuous source of moisture for the ice crystal, which absorb the water vapor and grows rapidly. So ice crystal which can survive will grow at the expense of the evaporating water droplets. So during an ice crystal process, ice crystals grow larger at the expense of the surrounding water droplets. So the constant supply of moisture to the ice crystal allows it to enlarge rapidly, and at some point it becomes heavy enough to overcome the updrafts in the cloud and eventually begins to form. Considering a water droplet molecule and an ice crystal molecule, the number of water vapor molecules that is required for the water vapor molecule to survive, or the saturation vapor pressure of water, is greater than the saturation vapor pressure of ice. So for this ice crystal to survive, only this much water molecules are required at this temperature, whereas for the water vapor molecules are required for. So because of this, what happens? These water vapor molecules start move towards the ice crystal, and eventually, since the vapor molecules around the water droplet is decreasing, the saturation vapor pressure, the droplet will be out of equilibrium, and it starts to evaporate. And at the expense of, as the droplets are starting to evaporate, it is actually acting as a continuous moisture supply to the ice crystals, and eventually, at the expense of these water droplets, the ice crystals are growing, and as the ice crystals grow, at some point of time, it will grow long enough to survive the updraft which is within the cloud. It become heavy enough to fall down as precipitation. So as it falls down, also it kind of grows. So we will and there is some more process about it. So we will discuss about those things in the next class. So regarding the background condition process, we talked about ice nuclei. So two types of ice nuclei we talked about: deposition nuclei and contact nuclei. So in case of deposition nuclei, the water vapor molecules condense and directly form ice particles on these nuclei, and whereas in case of contact nuclei, these particles collide with the supercooled water droplets and then leads to the formation of ice. So ice nuclei is basically the same as cloud transition nuclei. This provide platform for the formation of ice. In cloud transition nuclei, they provide platform for the formation of cloud droplets. So but the amount of ice nuclei available are very much less compared to that of cloud transition nuclei. That's why the formation of ice crystals is difficult compared to that of the formation of water droplets. Okay. So I hope things are clear. So the precipitation process in case of warm cloud, the process is known as collision covalence process. So in the collision covalence process, the most important thing, the factors that actually enhance the process is basically the range of cloud in the cloud, thickness of the cloud, and the updraft in the cloud, and also the electrical charges of the cloud droplets. And work-ground condition process actually is the formation of precipitation in cold clouds. Cold clouds means which is having which is present above the which has cloud tops above the 0 degrees Celsius isotherm. Which cloud tops go up to height of minus 40 degrees Celsius. Those clouds are basically known as cold clouds, and the precipitation in those clouds, the precipitation forms by the process known as work-ground process. And in case of work-ground process, the fact that the saturation vapor pressure over a plane surface of over water droplet is greater than the saturation vapor pressure over ice crystal actually helps in the growth of ice crystals at the expense of the evaporation of water droplets. By this process, the ice crystals grow, and once it becomes heavier, it falls down. So I hope the things are clear. We started with stability. We talked about positive static stability, negative static stability, saturated adiabatic gas rate. And then we moved on to, and also conditional instability. What is the condition for conditional instability? We also learned what is the level of free conduction. And we talked about curvature effect. What is homogeneous nucleation? What is heterogeneous nucleation? What is cloud condensation nuclei? The mathematical expression for curvature effect. We also learned about Sylviev effect. Then Raoult's